need to ask, I think I've got 4, but there may be a possibility of getting a 5th one by hijacking the one that's mounted in the wall.
Okay.
And the
Should I CC Chris on that as
yes,
well?
please.
Okay.
All right. Ask me and I will, if you haven't, actually just ask me and then I will CC him on saying, yes, you've got that one too.
Okay.
And then I'll wait for him to browse it.
All right.
Should we speak to Aaron real quick?
Yeah. Yeah, we should.
Did you see Did you see my emails that I was exchanging with Pedro about?
Oh, yeah, look, good advice, it looks like.
Okay, cool. Yeah, just wanted to. They have.
Yeah.
Want to. I don't want them just to go off down a rabbit hole of making like a 423 simulation. But
Yeah.
here's what would be useful for the team. So like, kind of high level saying what would be useful, how they can be used for that, but don't actually go and make it because that's not a 4 or 5 project.
Yeah.
That was so funny. Is any of you use Surface, by the way? Like, I forget my pen, so. Okay. I guess it's gonna be a bit hard. Okay, so today we will talk about MaxFlow, how to solve MaxFlow in nonlinear time. So, like during the time when I was a PhD student, this is like a kind of out of reach. No one would have thought that MaxFlow can be solved in nonlinear time. And then, because like even in a unit capacitated graph, the best known time was something like m root n. This is based on blocking flow. And this is just the best known for like 40 years or something. Like this is from really old time, something like 85 by Robert Tarjan and something like that, and Slater and yeah, I'm not sure who, sorry, but and like it is exponent of n to the 1.5 is just there for a long, super long time, and until sometime like in 2010, it turns out that there is some algorithm that gives you approximation, 1 plus epsilon approximation, but the running time is now something like m to the 4/3. So given that this natural barrier of 1.5 is broken, people have tried, and sometime around this, there are two different groups. One is Sherman, and another one is Kerner et al. They managed to get approximate MaxFlow in linear time. And today I will show you this algorithm. The presentation of the paper by Sherman was actually hard to read. Like even until now, I think like very few people understand it. But given that you have learned everything in this class, you will see that this actually can be understood, and it's not too hard to present. So
what's the time of the?
Both of these is nonlinear.
Okay.
So actually, the running time that is shown in both of the algorithm is this, but it can be improved further to nonlinear. Yeah. And this is by Peng. Okay. So just to recall some terminology about flow. So yeah, we will, in this class, we always look at underrated graph, okay, with capacity. And like before, I think of flow as something that is quite flexible. It's just a vector such that flow from U to V is a minus of flow from V to U. And the flow has support, like on the, if U and V is not an edge, then the flow must be 0. Okay. And we talk about congestion like before. Congestion is just like the maximum amount of flow compared to its capacity, right? If the congestion is at most 1, we say that the flow is feasible or it respects capacity. And I will talk about this too, like the net flow that go out of a node is just summing over all nodes incident to you, and you sum all this flow from you to other people. Okay. And the demand, like D, I used to write demand as them, but this class I just write it D. So demand is just the amount of flow that should be sent out of the node, right? So I said that given the demand D, I said that this flow satisfies the demand if the flow out of U is exactly the demand. And we can talk about the total demand. It's just D of S is just the sum of the demand inside the set. So note that it only makes sense when the total demand is 0, right? Yeah. And we would assume this. Okay. And here you see it from homework that if we know that the demand is such that the total demand from any set is just at most epsilon times the cut size of S. And if this is true for every cut, then it means that there is a flow with congestion just epsilon that satisfies the demand. And this is proved by min cut max flow. So in particular, when you think of epsilon as 1, basically if the demand on every set is at most a cut size, then I say that D is feasible. It just means that there is some feasible flow that, like D can be satisfied by a feasible flow. Okay, so that's just the terminology. And now let's go to the problem. The problem that we will look at is this. You are given a graph, right? You're given a graph and the demand. And you either want to say that, like if you want to solve this exactly, you want to say that, okay, either this is possible or not possible. So if there is a cut, which this is the case, then it means that there is no feasible flow to satisfy this demand. Yeah. And otherwise, like if it is exact, you would like to just find a flow that is feasible and satisfy the demand. But here we have some relaxation by saying that this flow, instead of it is feasible, it has some small congestion, 1 plus epsilon, and it still satisfies the demand. Okay. So this means that no feasible flow satisfy D. Okay. And so this is a goal. We want very good approximation. But actually, if we and it's not clear at all how to solve this one. But actually, if instead of 1 plus epsilon, I allow like a very big approximation like M. If I want just M approximation, then actually this problem can be solved easily. And I will not tell you how, but the basic way is just you compute a maximum spanning tree in the graph. And then when you have some demand, you just route through the tree just ignore everything else and route through the tree. There is just a unique way to route the demand in the tree, and this will give you M approximation. So maybe we discuss this in the exercise session, but you can think about it too. It is similar to like a Y maximum spanning tree is a floor specifier of any graph with quality M. Yeah. But anyway, if you want very bad approximation, you can do it. Okay. And now, okay, we have this problem. Either find a cut or like find a cut or find a flow with some small congestion. The first key idea to solve this is that you change the problem a bit. So the problem that we will look at, before I define the new problem, let me define some new definition. So suppose that I have the demand D. I have demand D and the flow F. So think of you have demand and you try to route some flow already. And think of suppose that this flow doesn't really satisfy the demand exactly. Okay. Then it makes sense to define something like called excess or residual demand. I think of it as the same thing. To be such that the demand D after routing F here of V. So excess at V is just the remaining demand minus the flow out of the node. Okay. So that's the excess or residual demand. And now I can define some notion that what does it mean by F almost satisfy the demand. Here I would say that F epsilon satisfy D if the residual demand is so small. And what do you mean by that? The residual demand for every, like the total residual demand on every cut S is at most epsilon times the cut size. Okay. And just from this definition, what does it mean? It means that actually there exists like a way to augment this flow. There exists F oct with just congestion at most epsilon, such that if you augment F with F oct, then this guy satisfies the demand, right? So it's possible to just increase the congestion of F by other flow just by epsilon to make it satisfy the demand exactly.
Could you say how you define the demand function again?
Yeah. The demand function is just any number, like it just assign any number on each node. But you should think of like the total demand should be 0. That is, maybe S have 10, this guy have minus 10. But it cannot, like it might not be just 2 nodes. It can be everywhere. But
Same as in the homework.
yeah, same as in the homework. Yeah. Okay. So this is very important. So question about this definition, that F satisfy, like epsilon satisfy D.
We need delta S, like
Delta S is the cut size of S. So when it means this, right? Like after routing F, there are some residual demand, and this residual demand is small for like is small in this sense. That is, for every set S, this total residual demand is small compared to the cut size. And this just means that there exists f arc such that like f arc satisfy df, the residual demand with congestion epsilon. But because this guy satisfy the residual demand exactly, it means that if you just add this f arc into f, then it's actually satisfy the original demand exactly. So if F0 satisfy D, then that just means that it satisfies the demand exactly. Okay. Question about this definition?
So if we find an f such that epsilon satisfies D, then are we done at that point?
If you really find F that satisfies D exactly, you are done.
No, if epsilon satisfies, because then like f augmentation, it should not be that difficult to find, right?
Yeah, that's the intuition. Like F augmentation. Like if you wanna just some relaxation of F augmentation, that shouldn't be too hard to find, and that's exactly why we're gonna like show that the following problem is enough. Like it suffices to solve the following problem. So let me tell you this new problem. That is, it's just that it's the same problem. You're given a graph and the demand. Now you just either find a cut, like before a violating cut, or now you find a feasible flow. Now this is feasible, no congestion, but it only epsilon satisfies the demand. And now I want to claim that indeed, like Nikhil said, if you want to solve approximate max flow, you can solve it just by calling this almost route subroutine log n many times, and you need just like a linear additional time to solve the approximate max flow.
Why should this be easier intuitively? I mean, it's just, I mean,
Yeah,
we started with some demand and we went to some other demand.
Yeah, you see. Yeah. So here. So the point is that you get some new demand, but now you can try to maybe look at the proof here. Yeah. So suppose that you are given a graph here. This is just a graph and the demand for the approximate max flow problem. Now I just call this almost route on this thing. If it returns me a cut, that's what we want. We are done, right? So let's assume now that it returns you some feasible flow, F0, that epsilon satisfies D0. Now I want to really construct the flow that satisfies D0 exactly, but with some small congestion. That's the goal. So, yeah, just look at this residual demand. And now, let me try to call this, like think of this residual demand as something super small. It's just like, it can be satisfied by some flow that have congestion just epsilon, right? This we know. So it makes sense if I just scale down the graph by epsilon factor 2. If I scale this graph by epsilon factor, they would still be still exist a feasible flow in this graph. So I scale it down and call like try to almost route D1 in this graph after scaling down. Can we get a cut? The answer is no. Just because we know that it is feasible. So you know that you will get a flow for sure. You get a feasible flow, F1, on this scale down graph that epsilon certify D1. So in particular, F1 has congestion. Like it's a feasible flow in this graph, so it has epsilon congestion in original graph. And what do we know about this? The residual demand of this residual demand. So we have that this thing will be at most epsilon in this G in this scale down graph, right? So this thing actually is just this. It's just epsilon square here. Okay. So you get again like residual demand of residual demand that is even smaller. Like now it's epsilon square. So what should we do next?
Again, define the graph similarly.
Yeah, we get like residual demand that is like now let's look at this residual demand of residual demand. Call it D2, and we know that this guy can be routed with just epsilon square congestion. So again, you should get an idea. You just can't try. We make progress now, right? We can look at this graph that you scale down by epsilon square and try to route this graph, this demand. You get F2 that on this scale down graph and so on. So F2 will have congestion epsilon square on original graph, and you get another residual demand in the further level, and so on. So suppose that I will just repeat this for log n iteration, right? So just repeat this for L level, where L is log n. Then you would get like and when you call almost route in this like a scale down graph after L iteration, and you get like residual demand of residual demand of residual demand and so on. So let's look at the total flow that you have tried to route so far and sum them up, right? What do you think, like, what is good about this?
It's exponentially decreasing.
Yeah, like it is like exponentially good, right? Like it become better and better. So in particular, I can first of all I can say that F itself here has congestion just 1 from this guy and epsilon plus epsilon square plus epsilon to the L. Like this is the total congestion of this total flow, which is still like 1 plus O of epsilon. But now this total thing would satisfy your original demand in a very accurate way. Not exactly yet, but it's like e to the L, and L is like log n. So this is like a, you can, when log n is big enough, you can think of this as any like, this is like any polynomial, like 1 over any big polynomial. Okay. Does this make sense? Like these two things. Like there is an algebraic proof, but I will not go into it. Yeah. So you have that epsilon to the L satisfy D0, where this is like a n to the 100, something like that. So in particular, we know that this residual demand after this after you round this total flow F can be satisfied with very small congestion. But now it's like if we really want to certify this thing exactly, we know how to do it actually if we allow super bad congestion. So let's look at this F final. Like given this demand here, if I know that it can be satisfied with this congestion, I can find some flow that satisfies this demand with m times this thing. And the reason is that we can use this maximum spanning tree. Like it's certified of like if you round flow via maximum spanning tree, it would certify the flow exactly, but maybe the congestion blow up by m. But here the congestion is so small anyway, it doesn't matter. So you can route this the like tiny demand with F final, and the congestion of F final would still be like negligible. So what we need to do is just now return F plus F final, right? And the congestion is small. Questions?
So I forget what you showed was the almost root algorithm, or was that used as a subroutine in between?
Yeah, so let me recall. So almost route, it either find you a cut. It either find you a cut or it return a feasible flow that epsilon certify the demand. So note that so what we do is just call this subroutine first for the first time. And if we get a cut, we are done. And if we don't get a cut, we design the log n many instance of problem such that every time that we call from now, you know that you get a flow for sure. And you can combine this flow together so that at the end it satisfies the original demand in a very accurate way.
So F1 plus F2 up until FL plus F final equals the F augmenting flow. Is that correct?
It should be F0.
F0 plus F0 up until FL, the summation of this plus F final. Is that the augmenting flow?
That's gonna be your whole flow.
Oh, okay.
Yeah.
See.
Like so actually you think of F0 is gonna be, in this case, sorry, this F here is gonna be F0,
Yeah,
and
it
F,
makes sense.
this is like F1 plus FL plus F final.
Yeah.
Right. Yeah. All right. So now we have our new goal, right? Either find a violating cut or almost route the demand. Okay. So now there is something that looks bad for this goal actually. This is because how can we even guarantee that epsilon certify demand? because this is about like exponentially many constraints. So it doesn't look so good. Okay. And this is what motivates the first ingredient that we will use. It's called congestion approximator. So here before I go into the definition, these constraints, there are like 2 to the n constraints you need to check. The question is, actually, can you find some small number of set, like some small family of set, that is kind of a representative of this 2 to the n? Like can you just enough to check that this condition is true for this not too many set and you're done? Can that be possible? So that's what congestion approximator is for. So I say that congestion approximator of G with quality Q here is just a family of cuts. Okay, not 2 to the n cut. It can be like much smaller than 2 to the n cuts, and it's a very good family because if you are given any demand vector, and suppose that you have checked that the total demand is small compared to the cut size, only for the cut inside this family, if you know this, then you know that this thing, like, it is true for every cut here, but maybe up to Q factor. So why it has something to do with this thing? So suppose now that you have checked that actually this demand is at most epsilon over Q cut size. And this is true just for like every guy in this family, then you know that this thing gonna be at most epsilon, right? So that's why that's how it should be useful. So before I go to it here, let me. So I'm gonna claim that actually, like suppose, like given, I'm gonna show that this cut approximator, like congestion approximator exists. Okay. So it means what? Actually, if you are given a cut approximator, congestion approximator with quality Q, and if there are just n many cuts in this approximator, then we can reduce the goal further, right? You can either find a cut, the violating one, or you just find the flow. Just find the flow here, such that this is true just for all set in the cut on the family. Because once you know this, you know that F would epsilon satisfy the demand. So now this goal looks like much more like manageable. There are just n cuts that you need to care about.
But can you think of it as in this way? The trade-off is that so epsilon over so Q you're thinking as something which is
Like polylog.
Yeah, so you need to say that it is much more satisfying.
Yeah.
For these small cuts, small number of cuts.
Right.
But
It
you're
should.
getting the output that for all cuts it is satisfying a bit more with
Yes. Yeah. So we kind of focus more onto this family, make the residual demand on this family very good by a factor of Q.
Yeah.
But now you're done for the whole thing. Like in other words, just want to find a violating cut, or make sure that the total access on every set in the family is small.
But do we know that such a flow always exists? Like you're asking that for some families what we know is that there's some, like if you scale everything by epsilon, then there's a feasible flow or something like that. But now we're asking that on these families we need even better. Do we know that such a flow exists?
So what we will do is that we will make sure that this thing happen, or otherwise we will find a cut. Yeah. So if it doesn't exist, we will find a cut. Yeah. Okay. So if you have congestion approximator, you're good. But now I need to convince you that actually it exists. And before I tell you why it exists, let me give you some example actually. So, and this will be an exercise you can try to do yourself. So if your graph is just a tree, so maybe it's 3 like this. Then actually you can define like a n-1 cuts. That is just defined by each tree edge. Like if you cut one tree edge here, it defines like this cut. And there are like n-1 way to cut in this way, like using a tree edge. So it turns out that just this cut is already a congestion approximator of a tree with exact quality. So, and like the intuitive reason is this. Suppose you have some demand, and to get a mean cut in a tree, you know that so how to convince you this?
If it is more than size 1, then it's like maybe there are like 2 connected components on one side. And then we can route the first component to the first edge and the second, or something like that.
Yeah. So yeah, I don't know how to give a good proof for this actually. The thing is just like when you suppose maybe that the demand is two nodes, then you know that the flow is just through this path for sure. That's the only way. And what you need to check is just like what is the minimum congestion along this path. But all of this cut is already included in this family, right? So at least it works for like a 2 nodes case, like ST demand. You can try to think why it works for any demand. Yeah. And if a graph is an expander, then the family which is just a singleton cut for every node, that would work too. So basically it's super simple in expander. You just take a singleton cut. So maybe let's do this in exercise session, maybe. But if you have any graph, actually, you can define, you can define a congestion approximator if you have a 3-flow specifier that we get from, that we show from last class. So let me say that T is a 3-flow specifier of graph with quality Q. So you have 3, right? And this is a 3-4 specifier, so the leaf actually correspond to the node of the graph. And then given any node U here in the tree node here, you can define a set SU. Sorry, SU is just all the leaf below the subtree of U. Okay. And then the cut approximator is just defined by this. For every node, tree node in the tree, flow specifier, take this SU. Okay. So it's really actually from this tree you get a laminar family, and this each set in the laminar family is just your congestion approximator. And the quality of this guy is going to be Q, just like the quality of the 3-flow specifier. Okay. So let me try to prove why it is a congestion approximator, right? So all we need to say is this, right? That is, given any demand on the vertex set of G, to say that this family is a congestion approximator, we need to say that if this demand is small compared to the cut, but only for every cut in the family, then we need to conclude that this is true for every cut. Okay, and there will be 2 steps to do this. I will say that given this thing, that the demand is small on every cut in the family, then I will show that it means that this demand can be routed in the tree. And if you can route the demand in the tree, you should be able to route it in G too, because this tree is a flow specifier of G. Okay, so let's do it one by one. So for the first step, suppose for contradiction that although this is small, although this is true, let's suppose for contradiction that D is not feasible in T. You cannot route it in T. If it is not feasible, just by metformin cut, you know that there exists a cut U such that the total demand is larger than the cut size in the graph in this tree. So the cut U might look like this, right? But what's the cut size of this guy? It's just this one plus this one plus this one, right? So what I claim is that, so from here you have that actually, and let me say that this is like So just from this example, you have the following, right? You have that SU1 plus D of SU2 plus D of SU2 U3. This thing must, like, if you take like absolute value of each subtree here, like of the demand in each of these subtree individually, this should be just more than the demand in U, right? But this thing is more than like the cut size here, which is more than the cut size of S1 plus S2 plus S3. So first of all, like, I claim that the capacity of this edge here is gonna be at least cut size of SU1 here. Why is that? This is because the tree is a flow specifier. So anything that it can be flow in the graph must be like anything that can be routed in the graph must be routable in T too. Like, or like a cut size in the graph must be at least cut size in the tree. So like that's why like this thing needs to be at least the cut size in original graph. And that's why this thing is at least this plus this plus this. But if this whole thing is more than this whole thing, it means that there must exist an I, like just one guy such that one of this is greater, like one term here is greater than this term. So is this clear? Like the important thing is to note that like each of this guy here, like the capacity of tree edge from U to its parent must be at least this. And this is because the tree is a flow specifier. Once you have that, just combine this inequality, you would have that there must exist just one node U such that the total capacity is more than the cut size. Question about this? So that's the first step, right? So the first step is that if this is true, that is, it's just enough to check. Like you really just check if for every U here, you just check if the total demand inside is more than the cut size here. That's all you need to check. If this is the case, then you know that D is feasible you can route D in T. And now if you can route D in T, you should be able to route this demand in G too with congestion Q. And intuitively, this should be very believable. Like it's almost immediate, except like some syntactic thing that you need to check, because tree flow specify is about multi-commodity flow, but the demand here that we talk about is about the demand for like a single commodity, right? So, but besides this issue, then intuitively, anything routable in T should be routable in G with congestion Q. Okay. But let's verify it anyway. So suppose that you know that you can route this single commodity demand D in the tree. Okay. So let's look at the flow that the feasible flow in T that routes D, that satisfy D. So well, the flow gonna look like something like it might look like this plus this thing and so on. But then you can decompose this flow into flow path, right? Like let F, capital F of T be like the set of flow path. After you decompose this flow Ft, you just get a bunch of flow path. And you can think of this set of flow path as multi-commodity flow. Like each path is one commodity for itself. And you from this flow path, you can define the multi-commodity flow demand that this guy route, right? That is, like if you have the flow path here, then you can say that okay, and this is like a 2, then you can say that Dij is 2. Look at another flow path, maybe this, and this is k, and this is 3, then djk is 3, and so on. So just look at this flow path. You can define multi-commodity flow demand. And just because this, and you can say that like this multi-commodity flow demand is routable in T just because of Ft. But now we can really talk about multi-commodity flow demand. Yeah. Everything here I just do so that I can talk about multi-commodity flow demand that is routable in T. And now, just from the definition of tree flow specifier, if you can route multi-commodity flow D in T, you can route this thing in G as well with congestion Q. Okay. So you can, and by routing D in G here, you route it as a multi-commodity flow. But if you can route multi-commodity flow demand with congestion Q, it just means that you can route it as a single commodity flow with congestion Q too. Because when you think about multi-commodity flow, you have many commodity that the flow cannot cancel. Now, like, just look at kind of the same demand, but now it's single commodity. Now the flow can cancel. The congestion can only get better. Okay. So if D is now routable in G, then the original demand here is routable in G too. Okay. And the details is here, but question about this? All right. So now, what do we have? We have that D is routable in G. Like, if you can route in T, you can route in G with congestion Q. If you can route in T, you can route in G with congestion Q.
So the flow path decomposition we did in T, how we do it doesn't make any difference on whether it is possible or not?
Sorry, can you say again?
So we are now creating that tree decomposition. The flow on the tree, we are decomposing it into parts.
Yes.
So should we do it in an intelligent way, or any naive way of decomposing it also will?
So given a flow, you can decompose it into parts in a unique way. So, and here I really just talk about the existence. We don't do it algorithmically in this proof. Okay. And just from this part, you can define multi-commodity flow demand and so on. Yeah, you get multi-commodity flow demand in T that is routable, and you get it means that there exists the flow that is routable in G as well with congestion Q. And you just and that flow is still multi-commodity, and you just made it single commodity. And that flow will just gonna route D here. Yeah. So if D can be routed in G with congestion Q, it just means that this is the case. Right? So now we are really done proof. We are done with the proof. If this condition is true for every guy in the family, then the condition is true up to Q factor for every cut. So yeah. And if you use a state-of-the-art algorithm for tree-flow specifier, then you're gonna get congestion approximator with quality Colilog. And the number of cuts in the family is at most 2n. Why is that? Because the tree has leaf at this node, and the tree edge can be just 2n minus 1 at most. And the algorithm like this, the best algorithm here can construct this tree-flow specifier in linear time. So you get congestion approximator in the same time. And actually, you know something more that actually might be useful to think about. Because the tree-flow specifier, everything that is known in the literature actually has depth just log n. So it means that every vertex is contained in at most log n set. So there are no like a very nested part. Okay. So this is just by using the best tree-flow specifier, but we have seen one tree-flow specifier from previous class as well. So that is to use expanded hierarchy. So in that class, I kind of just talk about unweighted graph, but everything just extend to capacitated graph too. And the quality was something like n to the little 1, if you remember. And the construction time is gonna be can be made like fast too. So at least you see how to construct such a congestion approximator with slightly worse guarantee, but the better one is known. Okay. So let me just assume this for this class. Okay. Again, we have construct tree-flow congestion approximator, and the goal is to either now we either want to find a cut, a violating cut, or find a flow that has very like small excess on everyone in the family. Okay. Now comes the second ingredient. So the first ingredient, congestion approximator, is pretty amazing, but it just exists because of tree-flow specifier. this is another ingredient that is quite amazing that it exists too, but I will just state what it is. Yeah, I will not give a proof. But yeah, I taught this in my previous class, and you can have a look in the video lecture of that previous class. So this is called multiplicative weight update. So it's a framework for a lot of things. One of the things that it can be used is for solving LP. Okay. So just consider this LP. Like the goal is you're given the constraint matrix A, and like you are given AX at least B, yeah? Where A is a matrix, B is a vector. You want to find X such that AX is at least B, and X is in some convex set. Maybe think of this as just anything positive. That's one example, one canonical example. Or think of X as between 0 and 1 for all coordinate. Okay. So we will think of this as a hard constraint, and this, I just said that it's something easy. This is, you think of it as hard, and this is easy. And the goal that we want to do is that we want to relax the goal a bit. We want to just find some X bar such that it just approximately satisfies the LP by some additive factor. Like all the hard constraint here, you just want to satisfy up to an additive epsilon for every constraint. But the easy constraint you want exact. So this is the problem. And the multiplicative weight update allows us to find this such an X. If by only like, if you can just solve the average problem for a few rounds. So this average problem is going to be much easier, and but you just need to solve this much easier problem for a few number of rounds, and then you solve the problem. Let me be more precise. This framework is such that there will be rounds. Like there will be like round. Start from round 1, 2, and so on. In each round, the framework will set some weights to each constraint. Like we call that there are n many constraints here. So think like this as XA, and this is X at least B. And there are n many constraints here. And the weight is for each constraint. Like for each constraint, there is a weight, Pi. For each of the hard constraints. And once the framework, think like this, you are working with a framework. The framework gives you some weight, and what you need to do is to solve the average problem defined by this weight. And by average problem, I mean that it's this thing. So it's like all the hard constraints here, you just sum them up with some weighted average. You weight it by P and you sum them up. From n constraint, it becomes just one constraint. So much easier. So all you need to do is that you have just one constraint and one easy constraint. You need to solve this problem. Like in each round, the framework gives you the weight. You solve this average problem. And suppose that you can solve this problem. Like
For every round, we'll have a different x which satisfies.
yeah. In every round, you will find different x. Yeah. So like, given this problem, you just find this feasible solution xt for the average problem of round t. So that is, this is certified and this is certified. But actually you need a bit more, you don't just solve average problem only. Actually, you also want to say that this xt has something that we call small width. Has small width. The width is at most row. And what do I mean by this? I mean that X does not violate or over satisfy each of the original constraint by too much. So that is, if you look at the ith constraint here, X times the ith constraint minus bi, this is not too big. Like it's not violated by too much, and it is not like it does not satisfy also. Okay. So I want this to be true. So that's the goal for your task for each round. The framework gives you the weight, and you solve this average problem. It's much easier, but you also need that it doesn't violate the original thing by too much. Okay. And once you have,
Doesn't this give extra n constraints?
yeah, it's like some extra constraint here that you need to. So yeah, you need to guarantee this too. Yeah. So it's like now actually there are 3 constraints. Yeah, this one, and also this one.
Is there n, right?
Yeah.
So we have n plus.
So yeah, you see that it's gonna be easy to do. Yeah. Because like you can violate it in both ways, and you just need to like upper bound it. So yeah, but you're right. This is like a n mini constraint. And now, once you have solved your problem, like once you have solved the average problem, you get xt. Then the framework will adaptively update the weight somehow. And actually the way that it updates is something super simple, and it's quite intuitive too. So it will update in this way. Each of the weight will be multiplied by some factor. And then you go to the next round. And the intuition why this makes sense is the following. So if the ith constraint is violated a lot in round t, so that is this thing is just much smaller than b, right? Then this is gonna be big. And then the weight of the ith weight will be increased a lot. And in the next round, like you kind of put more importance into this constraint. So it makes sense that the next round, maybe the ith constraint shouldn't be violated by too much again. So that makes sense, and actually, like it works. um, just few word about this thing, this is the algorithm that is rediscovered so many times and is super powerful. It is used in for algorithm, fast algorithm like this. It's used for complexity theory to construct some pseudo-random object. It's used for machine learning, for online learning. I think Nikhil teach this. It also occurs in nature, the way it explains something in biology, basically. The way that the gene updates its strategy somehow correspond to the way multiplicative weight updates. So it's something that it seems to be something that people discover. It's not something that people invent, I think. So it's very cool. Yeah. Anyway, so the framework will update the weight in this natural way. And all you need to do per round is to solve this average problem. And what it says that the guarantee is this. Just this many rounds. After this many rounds, something like width square. And you should think of width as constant, actually. Log n rounds, basically. Then if you just compute the average of everything that you have found so far, this thing gonna be what you want. Somehow the weight on each round are updated in such a way that although in each round you don't satisfy every constraint exactly, when you average them together, at the end it will satisfy every constraint up to additive epsilon.
How much time does that easier version take in each round?
Yeah, now it depends on each problem. Given any LP, you get some average problem. Now it's specific for each problem now. And we will see that in our case, the average problem is some particular problem that is super simple. Yeah, but this depends on the problem. Depends on the LP here. Okay, so now we have all the ingredients that we want to look at. So just to recall, the goal is to either find a White-Leading cut or a feasible flow such that small excess on every guy in the family. And if I rewrite things a bit so that this looks like an LP, so let me simplify this to epsilon prime. Okay. And we can write there is an incident matrix B, which is defined like this. So B is such that there are n guys here, and each of these correspond to an edge. And even edge is even edge between U and V, then you put a 1 minus 1 in this column. Okay. And everything else is 0. Then, so you are familiar with incident matrix, right? Yeah. Then note that if you multiply F, B to F, and you look at the node, you have F here, and you multiply it. The sum here, the entry of V at B times F is just exactly F out. So I'm kind of almost out of time. Okay, maybe I will just finish when I state the LP. Yeah. So this, please verify it, maybe. Yeah. And now let's write this indicator vector 1 of S2. And now you can see that the constraint here can be written in this way. That is, it's just like, so df is nothing but d minus f, right? For every node here. Yeah. So you can, sorry. Df of v is just dv minus f out of v, which is dv minus vf v. Yeah. So basically, this as a vector, you can write it as this thing, and you sum over all node in S. So this is the same thing as multiplied by 1S. And you want this to be at most this. But you need to have another side of the constraint too, because this is in absolute value. So you get this thing. That is, this is at least minus epsilon times the cut size. And now, because the multiplicative weight update is about additive error, so I want to write it down like a additive, like as an additive factor here. So I just divide everything by a cut size, so you get this thing, right? So the constraint that we have in the beginning here can be write down in the like a linear as a linear constraint, like two linear constraint here. Okay. So now we can rewrite our goal, that is either to find a violating cut or find a flow such that this is the case, is feasible. And for every guy in the family, you have the linear constraint we just write above, the two linear constraint. So now we get this LP basically. Find F such that these things are true. Two linear constraint and this done. And now this looks like something that can be applied by, like you can use multiplicative weight update to solve it, right? But we are out of time.